It's running.
Jacob, I believe you popped into the frame briefly there, so you have an alibi. All right, any questions? Oh, sorry, hold on. Just this. Okay, Lisa?
Yeah, I was having trouble on 2A, 2B, and 2C on this chapter, the 8, yeah. 8.
Okay, so you have a problem on problem 2?
Yeah, basically.
Small car, large car, same speed. All right, there's some things that are not stated that should sort of be understood. I am considering it a closed system. So momentum is conserved. That's what I'm going for there. So if momentum is conserved, what does that tell you?
Tell me that it's a closed system.
So is it closed? Okay. Anyone else?
It's perfectly elastic?
Not necessarily.
Is it inelastic?
Initial momentum equals final momentum.
Okay. So if I have two objects, this object has, I don't know, 5 units. So I have an object with, there we go. So this has 5 units of momentum, and this has, I said head-on collision, so one of them's got to be the opposite, so negative 20 units. What's my total momentum?
Would it be? Oh, it's negative 15.
Okay. So after the collision, what's going to be the total?
Negative 15.
All right. So if this has 7, what does that have?
That has negative negative 22.
So anywhere in here, did I specify what type of collision it was?
No.
Okay. So how much did this gain?
That gained 2.
How much did the other one gain?
Negative 2.
All right. So back to the question. Which vehicle experiences the larger magnitude of the change in its momentum?
So I would say that, wouldn't it be the same?
Yeah, it would be. As long as momentum is conserved.
So basically the same for each of them.
Yep. You want to adjust anything?
I think I'm
You good on that?
okay on that one. Yeah, I'm pretty sure. Yeah. I think I'm okay on that one. I do have a question on number 7 on, I guess, chapter 7. I just for some reason, if I see stuff in a different notation than I'm used to, my brain just shuts off. So there's 2 forces, the conservative force and the non-conservative force.
Right.
So would the J hat, would that just cancel out since one of them's 2, one of them's negative 2?
For the total force, yes, it would.
So the force would just only be acting in the 3 newtons in the I hat direction?
That's correct.
And then, so you have a 3 Newton force in the I hat direction, and then you're trying to find the velocity after 5 meters.
Speed.
Speed, sorry. How do you relate those 2 things? I just
All right, so I gave you conservative force and non-conservative force.
Mm-hmm.
So the total force would just be the sum.
Mhm.
Okay, so we're talking about the total force. Total force does total work. So the total work is equal to the change in kinetic energy. So speed is built into that.
Okay, yeah.
And I gave you enough information for force, and I gave you the displacement in the i-hat direction. Since this is gonna be the total work,
Times
sorry,
the-
total force,
Times the displacement.
times the displacement dot product. And so, since only the i-hat survived, I only care about the i-hat here.
Uh-huh. Okay, and then, so you'd be solving for VF. So your change in K would be 1/2 mv squared plus, or minus 1/2 mv initial,
That's what you're trying to find.
right?
I told you the initial velocity,
You did.
and so to find the initial speed, just do a little Pythagorean theorem. And make it three-dimensional.
Oh, you're saying, you have to do a squared b squared equals c squared to find?
To get vi squared.
You wouldn't just use the velocity that's in the i-hat direction?
No, because this is speed, not velocity.
Okay, even though that you're only concerned with the, well, I guess the others cancel.
If you did it that way, would you still come up to the same answer? So, well, we've done a lot of stuff where that just would work. I suspect that would work, as long as at the end of it, you then brought the j-hat component into it
Okay,
and did the Pythagorean theorem at the end.
gotcha.
Because that would be, yeah, I think it would still work.
But the force total would just be 3 newtons?
Yeah,
Okay,
in the i-hat direction.
right.
Yeah.
Okay.
And if I gave you, just as a side note, if I gave you initial velocity of 3 meters per second i-hat plus 2 meters per second j-hat plus 1 meter per second k-hat, how would you find the initial speed? If I gave you that with just the i-hat and j-hat, how would you find initial speed?
Pythagorean theorem.
Okay,
What would you do in this situation? You just do all of them?
3 squared plus 2 squared plus 1 squared.
Oh, okay. But it still works with
Yeah.
in 3 dimensions?
Yeah.
Okay.
It's easy enough to show mathematically, but it's not worth the time really right now,
All right,
unless you're desperate to know.
it's all good.
Okay. Ben?
Question 6 in chapter 8, the L part. What is the car's speed after skidding?
All right, if you know the kinetic energy after skidding, then you find the speed by setting, so whatever your answer to
I'm
part.
trying to find the speed first and then find the kinetic energy after.
Yeah, I sort of did it in the order which at least made sense to me, because you know what the initial kinetic energy is. So you know Ki, you know the work that is done. It's on a level surface here, so the change in kinetic would also be equal to the change in energy, since there's change in potential is 0. And so you were given the force, you're given the distance, and so therefore you can find the total work that's been done. Set that equal to the change in kinetic energy.
Yeah, I found the work.
Okay,
I found that.
so once you have the work, so that work is gonna be K final minus K initial. That you already found in part I. That you said you found, so solve for KF, and that's just 1/2 mv squared. I gave you the mass, I believe.
So I find the speed after I find the kinetic energy?
Right.
I tried to find the speed first and then find the kinetic energy.
Yeah, if you're finding the speed first, I think you would have to basically be using Newton's laws and then,
Can I find the speed first by using these numbers? Can I find the speed first by using?
I think it is possible. Because it gave you initial speed. I gave you the friction force. I gave you the mass of the car, so you should be able to find the acceleration of the car. And with the acceleration and the initial speed and the distance of the slide, you should have enough information to find the final speed.
I found something, but I'm not sure.
The biggest mistake I see students make on this one is they forget the negative somewhere. Recognize that it's sliding opposite the direction of the force, of the net force, or that the total work is negative, because the final kinetic energy is less than the initial kinetic energy. I don't know if that was your issue, but that was a mistake I see on.
Well, so would our speed be positive or a negative value?
Speed is a positive number.
Oh, yeah, 'cause it's, okay, I'm thinking about velocity.
If you end up with a negative velocity, that thing, you had it stopping and somehow that friction pulled it backwards, which would be really scary. You skid to a stop and all of a sudden you feel yourself getting dragged in the wrong direction. All right, let's take a look at some chapter 9 stuff. I have a rod pivoting about its endpoint. The rod has some mass M, we'll just say some length L, and spinning around at 2 radians per second. All right, let's keep it generic, omega. What is the kinetic energy of the rod? We'll start out with the formula. What's the formula for kinetic energy?
Mg squared, but.
Not quite the course that I said before, but
Would it be omega?
It's Omega R, right? Is it-
1/2,
V is omega R, I'll buy that. Pardon?
1/2 I omega squared?
Yeah, but what I'm going to do is actually derive that.
Oh,
So, yes, you are absolutely right. Let's see how we get there. So, if you want to do the omega R substitution, so because V is equal to omega R, we got 1/2 M omega R squared. So 1/2 M omega squared R squared. So what would you plug in for what? Okay, M is the mass, okay. Omega would be given. What would you use for R?
Well, you said it was pivoting about the bottom point of the.
Yep.
So it would be the length of the beam.
Okay, that will tell you what, so that makes the assumption that all of the mass is concentrated right here. Because that R is the distance that mass is away from the pivot point.
Oh, okay, so then it would be half L. Because we work with the center point of the,
So that point right there,
yeah, presumably,
why that point?
because it's the center of mass.
Okay. That will get you a crude approximation. Because if we think about it in terms of V, the point down here is not moving very fast at all. The point up here is moving the fastest. That is sort of halfway in between. That would be half the speed. However, that doesn't really get you Yeah, that's actually not the average speed though. Let's try that one again. That's the average speed, that's not the average speed squared. What can we do in order to get a better approximation?
Calculus?
Well, yes, that would work. Without calculus. And by the way, in the calculus-based course, I start in the same spot. We eventually get to the point where, and this makes it a calculus problem. But until then, if that's not representative of r squared or v squared, but it's a decent, well, it's an approximation.
Would we use some of the angular variables? Like, would we replace them since it's an angular problem?
We will eventually do that. But how do you find the average speed for an object where not everything's traveling the same speed?
You calculate the moment arm.
To where?
Well, the part that it's pivoting around is not technically shifting away from that spot, right?
Right,
It's staying in
okay.
that spot. So wouldn't, the part that's changing would be like just off of whatever that infinitesimally small spot is that is not moving. And then taking like the part that's moving the most, would we use and average those two pieces and somehow exclude the part that's not?
Okay, I'm gonna go with the spirit of what you're saying. In essence, start looking at parts of it and averaging parts of it.
Right.
That. So I'm gonna just start out with something a little bit simpler. I'm gonna cut it in half and look at the top half and bottom half.
Okay.
If you took that point just off the axis of rotation and the very end point, you're basically in the same situation as you are right now. So now we have this point and this point. If we can figure out the speeds of those points, I will make the substitution in the end. I'm gonna start here. So if I did in two spots, broke it up into two pieces, this would be 1/2 m of the first part, v of the first part squared, plus 1/2 m2 v2 squared. This will get a better approximation. How could we do better?
More points.
So in essence, what we're gonna head towards is, I'm gonna break it up into, let's just say n parts. N parts. And so it's 1/2. So I'm gonna add them all up. So it's 1/2 times the mass of one of those parts times the speed of one of those parts squared, and I goes from 1 to n. So I'm just gonna add them all up. Now, doesn't that make this problem so much easier? All you have to do is break it up into a whole bunch of parts and then add up, find the speed of each of those parts, find the mass of each of those parts. Perhaps there's a simpler way. Let's make that substitution, because there is one thing that is common for all of it, it's omega. So this would be the sum, I is equal to 1 to n, 1/2 m sub I omega r sub I squared. Omega is the same for all of them, that is common. We are making the assumption that this is a rigid body. This is not a valid assumption if it's not rigid. In other words, as the thing moves, I assume all of it moves to the same angle the same amount of time, as opposed to part of it lags behind as part of it starts moving and the other part does not. So this will end up being omega squared, but recognize here I have 1/2 and 1/2, it's a constant. I could just factor it out if I wanted to. So this 1/2 here is just 1/2 plus something, 1/2 plus so on. Omega is also a constant, so I can just factor them out. So this is just 1/2 omega squared times the sum MIRI squared. Now it's easier. This right here is the moment of inertia. if you take that piece and you break it up into an infinite number of infinitesimally small pieces, in other words, this mass becomes infinitesimally small, what we have here is just a quick 5-second aside. That would be the integral r squared dm. Infinite sum of infinitesimally small bits. If you haven't had calculus yet, don't worry about this. But what this makes our equation come down to is what Anna had said earlier, 1/2 I omega squared. Now it's easier. Let me grab the book. Oh, this is chapter 10, not chapter 9. All right, this is easier because this formula right here has been done for common shapes. In your textbook, it's page 357. Did I saw that correctly? Yep. If you look at page 357, and almost every beginning textbook in physics will have something like this, that's what it looks like. You have a formula sheet here for common shapes. So for example, if I have a solid sphere, I think they have solid in here. Yeah, solid sphere. Radius r, mass m. The moment of inertia formula is 2/5 mr squared. Now, in terms of the notation, typically in these formulas right here, they'll use capital M and capital R. Because recognize we're adding up a whole bunch of little m's and little r's here. Capital M is the mass of the whole thing. Little r, or capital R is the radius of the actual object itself, as opposed to of an individual piece.